Hello, my name is Eric Hixson. I'm the Vice President of Data Science and Methodology at Vizient, and I'm here with a colleague, Adam Hasham, who's the Director of AI ML Engineering at Vizient, and we are very excited to share a project that we've been working on regarding unifying AI architectures, addressing a common problem in a hard challenge. So before we dive into that, I'd like to share a little bit about Vizient and set the project context. Vizient's mission is to empower healthcare systems to deliver better care, operate more efficiently, and grow with confidence. Our members, next slide. Our members range from the largest academic medical centers to small critical access hospitals, and when combined, provide a majority of the care provided in the US. We achieve our mission by providing a number of tools and services to inform, to benchmark, and enable performance improvement. One of those tools focuses on clinical utilization and patient outcomes. Risk adjustment is critical for accounting for patient complexity, and that allows outcomes to be assessed and compared with confidence. With that backdrop, let's pivot to a common challenge many organizations face: moving AI out of experimentation into the real world, and those production environments where they actually deliver value. That's exactly the problem this work was designed to solve. At Vizient, we've been very intentional about shifting data science from a collection of isolated models and retrospective analytics into a strategic driver of enterprise intelligence that operates at scale with discipline and trust. We're organized as a centralized cross-functional AI and ML center of excellence, work closely with our product engineering and business teams. And that structure allows us to focus not just on building models, but on everything that comes after: deployment, governance, monitoring, and long-term sustainability. And that's where applied AI either succeeds or fails. Developing 2,000 models across diverse patient populations and use cases is meaningful, but scale alone isn't the hard part. The real challenge is operationalization. How do you reliably deploy models? How do you govern them? How do you ensure they perform as expected over time, they meet regulatory and ethical standards, and they remain trusted in a high-stakes environment like healthcare? This project directly addresses those questions. It represents a way to move from fragmented, one-off delivery patterns into a unified, production-grade framework for packaging, validating, promoting, and managing models across environments. It embeds lifecycle governance, centralized model inventory, shared ownership, and CI/CD-based deployment pathways, turning applied AI into something experimental into something dependable. It's also a concrete example of how applied AI becomes enterprise ready. Standardized platform integration, stronger accountability, reusable patterns, continuous integration, and faster time to production aren't abstract goals. They're prerequisites for scaling AI responsibly. This work puts those principles into practice and creates a governed foundation that supports trusted AI in real clinical and operational settings. Finally, it positions us for what many sessions here are starting to explore next: more connected, orchestrated, and eventually agentic AI workflows. By linking data, semantics, and execution into a coherent ecosystem, we're not just solving today's problems, we're building the infrastructure needed for the next generation of applied AI. With that framing, I'm happy to introduce Adam Hasham, who will show you how this approach works in practice and what it looks like to operationalize applied AI at enterprise scale.
All right, thanks, Eric. So what makes 2,000 models a lot different than a lot of models? Well, the challenge isn't just model count. It's model count under healthcare constraints. So these models represent segmented patient populations and outcomes. And this truly isn't needless duplication. But if promotion, monitoring, and rollback happen independently, the system becomes fragmented really quickly, especially at this scale. So on top of that, you also have other supporting artifacts like dictionaries, transformation formulas that must stay aligned to the model version. And this adds even more complexity, especially in healthcare, where the model architecture must be preserved for validation while still being maintainable. So coming together, this is a lot different. It's high stakes. Clinical trust is paramount, and we must consider patient safety, especially when our solutions and the models we are developing power operational decisions and benchmark that raise the bar of reality. Validation limits are also important. Models are validated by clinical teams, so they must be preserved rather than retraining or even revalidating per environment. And here, auditability is key too. Traceability, reproducibility, and rollback matters just as much as accuracy to maintain a high-performing system. So before we go deep into the design, let's just zoom out for 2 seconds. Why does this matter beyond this use case? So as Eric mentioned, these models are widely used nationally for healthcare. But what's really important here is the principles we use to solve it. So the ideas of unified delegation, of validated promotion, of a single model artifact for rollback at this scale are not just healthcare specific ideas. These are the same principles to deploy AI safely in any high consequence environment. So while this work started in healthcare, the broader outcome supports reliable AI deployment for high consequence environments. Before we go any further, let's cover some general AI inference patterns and use that to frame the problem. So at a high level, the inference flow is very simple. You can see in the first box that data comes in, and that's the model input. The data goes through processing and feature transformation, as shown here in the second box. The transformed data is then passed to the model, and the model will conduct predictions that will then go through post-processing before becoming the final output. So this is the basic pattern for model inference. And here we can see that the model could be anything from a regression model to a classification model to even something more complex like deep learning models and more. But the important part here is that this looks very straightforward, especially when you're thinking about one model or one inference path. Now, let's take that simple inference flow and multiply it across thousands of segmented models, each with their own transformations, routing, and lifecycle. So we're no longer dealing with one feature transformation path or one model path. We're dealing with 2,000 model-specific paths, each tied to different data processing, feature logic, and model behavior. And honestly, the complexity doesn't even start here. Post-processing can vary per model, and the routing logic here, as shown in the arrow, is essential. This is where the system determines which model path applies based on the input data. And on top of this, let's also keep in mind the AI model lifecycle. All these individual models and their supporting artifacts will evolve over time. So this is also a lifecycle management problem, not just an inference problem. So the question is, how do you deploy and manage this in a way that stays scalable, governable, and maintainable? Well, the first approach we can explore is the traditional deploy code pattern, which is shown here. So here, you promote your training and deployment code through your environments, and this is typically done through a release branch. But what you'll do is you'll execute the training, the registration, and validation separately in each environment, as shown here in these blue boxes. Now, this works well for very simple ML systems. And as you can see here, this becomes harder when you deal with 2,000 plus models. Instead of one validated outcome, you end up repeating the full lifecycle across dev, UAT, and prod. And this creates lots of operational overhead, especially around training, registration, and validation. This also creates a consistency challenge. So if the model training depends on the environment-specific data, configuration, or randomness, you might not end up with the same model artifact across all environments. And this is especially problematic in healthcare, where preserving the validated model behavior is critical. So While deploy code is a common pattern, at this scale, it introduces too much fragmentation and validation burden. The second option to consider is deploy models. So this is very similar to the previous model we discussed, but in development, we will still train, register, and validate the model. And this is exclusive to the dev environment, which is the first box shown here. Then what we'll do is we'll promote this exact artifact to the higher environments via CI/CD. And what this does is it preserves the model weight and configuration. So validation only needs to happen once in the lower environments rather than retraining the model per environment. This also brings a challenge, especially at our scale. You end up with 2,000 separate model artifacts per environment. And overall, this results in 6,000 plus artifacts across 3 environments. This is also including associated preprocessing logic and metadata that must stay version aligned. So while deploy code is a common and sensible pattern, it also creates a lot of operational fragmentation and overhead, especially when dealing with many models over time. So another approach we could take is taking the time to architect a unifying delegating model. And this takes time. You're front loading the engineering work that you'd alternatively be spending maintaining a lot of models in production. But this follows a similar approach to both the models we presented earlier. As shown in the first blue box, in dev, we train all the models. We'll register them accordingly. And the most important piece is we validate it, both with the model metrics, as well as doing clinical evaluations on the model. So in the dev environment, we'll end up with 2,000 model artifacts. And let's take a deep dive into one of these models. Say model 198 out of the 2,000 models we're training in the dev environment. And this is shown here in the middle with the model registry. So for context, perhaps model 198 could represent a specific subset of adolescents with a specific condition. And this model in particular could predict length of stay, readmission, mortality, or a combinatory of these. The model registry, which is shown here in the middle for this specific cohort, so model 198, would include the model version, alias, tags associated with the model, and some comments. They're more in practice, but this is just a simplistic example. Some important things to note here is there's 21 versions of this model. And what's key is model version 21 is up and coming model architecture in development. It's not ready for prod yet. And you can see that here explicitly in the comments. You can also see that explicitly in the alias where it is noted as the challenger model. The model 1 version below that, model version 20, has been clinically validated. And it performs well, and this is the model we want to use for production. This is marked with champion as an alias, as shown here in the red box. And this is the model version we want to package for production. Now let's zoom out and imagine this for 2,000 models in the developed environment, each with their own AI model lifecycle and interactions. Let that sink in. This is a lot of models, and each of these will have their own model registry to support the AI lifecycle and iteration for development as they refine to the final production model. Now let's construct the delegation model to encompass all these models. So this is shown here on the right. This will include a build script that automatically creates the model delegation object. In our case, we package the model using MLflow. So this is an open source AI/ML library for managing all AI models and their life cycles from classical ML to Gen AI. And the build script would contain a custom PyFunc script that defines the overall model predict, orchestration methods, and some custom logic for pre-processing and post-processing. This also defines the architecture of the delegating model, where we log files in the artifacts and scripts to encapsulate and support these methods. In our case, the pre-processing is custom per the model type. And as you can imagine, the features per model would change. So with more complex feature extraction, you can also separate that out into its own script for reference, which is shown here in the second blue box under the delegating model, to keep your code base cleaner. Model inference, which is also shown here, is another file in the model object, and this contains the model inference orchestration code. One thing that MLflow also does, it lets you package artifacts as well. And you can think of this as a directory where you could add serialized model files or CSVs for your model to reference. So important items to add here is that if you're doing this, you can include a model map, and this would map the models for each specific use case, a feature extraction map, which identify the features to compute per specific model, and a multitude of serialized model objects for reference as well. And this is a healthcare conference, so you can also include model explainability items too for each model if you wanted to package that together. So this gives us one orchestration model for deployment while preserving the full traceability and lifecycle of the underlying model. So with this delegation model, we can promote a single model artifact instead of thousands of independent models. Now, as shown in the first box in dev, we still train, register, and validate the full model family. So this would be the underlying 2,000 plus models would live here. But once complete and we're ready for production, we can build a delegation model artifact that would package the orchestration layer, the specific model versions of the 2,000 models that are validated and ready for production, the feature extraction and feature engineering logic, etc. Now, for the higher environments, instead of promoting the full model family, we just promote the one delegating model in each environment, as shown here in the last two boxes. So we'll have one model in UAT instead of 2,000 and one in prod. And we'll use this for inference workflow. And this is a simplification of the architecture. We train many in dev, and we promote one upward. Now let's compare the three deployment patterns against the constraints that matter the most for our use case today. So deploy code performs poorly, especially when you need to preserve model behavior across your environment. The retraining and registration per environment creates even more operational burden, inconsistency risk, and even more validation burden as well. The second approach we considered is actually a really meaningful improvement. This deploy model preserves the exact model artifact and avoids retraining in higher environments. However, at our scale, this leaves us managing more than 2,000 separate deployment units with supporting logic and metadata as well. And this creates a real challenge for maintainability, monitoring, and even long-term operations. Using the challenger champion approach can also be important too, even with the delegation model, and can simplify operations extensively. Lastly, unifying operation simplifies your operations overall. Centralizing the behavior in one layer versus many makes it a lot easier. So what we built isn't a way to just serve healthcare models more efficiently. It's a reusable framework for deploying AI models reliably in high consequence environments. Some things that are really important is that it's scalable across segments. With new institutions, next-gen model architectures, what we can do is create separate delegating models without rebuilding the entire approach to support this. It's also a flexible approach to support different model types too in one artifact. So we can support more complex models without retraining in every environment. And different model types can live together in the delegation model, which also makes it really powerful. Lastly, operating control becomes reusable. Testing, promotion, observation, and rollback are not one-off solutions. These are durable capabilities reusable for future healthcare AI systems. So this isn't just one healthcare use case. It's a repeatable framework for scaling AI, with reliability, with traceability, and with operational discipline. And with that, I thank you for your time today and would love to open up to any questions.